Так, всем добрый вечер. Давайте вновь поприветствуем нашего спикера, поаплодируем.
Thank you. Welcome to my talk about 5 boring performance improvements in MongoDB 3.4. So there are 2 questions. Why are they boring? In 3.4 we improved several things that have been quite painful for sysadmins and DBAs on the operations side that now become faster and complete faster. So they make DBAs' lives better, but they don't give like better performance, like benchmarking results or something that you can use in marketing. So actually our marketing was completely uninterested in this. I think, and knowing many of our actual users and customers, they are quite a big deal, so I like to talk about them. They are also boring in the sense that from programming, like from a development point of view, many of the improvements are actually quite trivial. Like in some cases use multiple threads instead of one, or use one thread instead of multiple, or something like this. But the significance for the operating of a MongoDB cluster is huge. The other question is, why are you talking about MongoDB 3.4 and not 3.6? 3.4 is still the most recent stable version, at least for some weeks. I will actually mention a couple of things that are in 3.6 as well. But this was a theme that we focused on in 3.4, and it's kind of topical for HighLoad as a conference. So I'm kind of glad that this talk was still chosen, even if maybe some weeks from now everybody wants to hear about MongoDB 3.6 instead. Oh, sorry, the other way we should go. So my name is Henrik. I worked for MongoDB now for almost 5 years. I spent many years working as a solutions architect. So I worked with a lot of customers in Northern Europe, including a little bit in Russia. I live in Helsinki myself, so I'm kind of I'm close to home at least, closer than many of your other international speakers. And I'm third time in HighLoad, so I actually enjoy coming to this conference. I'm happy to have been invited to speak. Before MongoDB, I worked many years in the MySQL world as well, so I've become a bit of a database person now. But last year I actually got the honor that my patch to Linux kernel was accepted for a device driver to make the webcam of my son's laptop to work. So now I'm really a full stack developer because I've also been a Drupal maintainer when I was younger. So I've done. Yeah, thank you. I think if you have committed to device drivers, then you are a full stack developer. So what we will talk about in this talk, faster initial sync when you add replication nodes. Then moving the balancer process to the config server, so it became a singleton. Wire level compression. Removing throttling from the shard balancer, which is like the same balancer as in number 2. And still with the balancer, parallel migrations between shards. So those were the 5 improvements in 3.4. And then I will mention some other improvements, which actually 2 of them have now been implemented in 3.6. So faster initial sync. So just to make sure everybody even understands what we are talking about, what is this initial sync? So in MongoDB, replication is it's not just about the fact that primary has a log of writes that have been applied, that then the secondaries are replaying, but there is also automatic failover, and also if you want to add more nodes, the first thing, of course, you need to do, you need a full copy of the database on the secondary as well. And that is also automatic. So you just kind of install a new empty MongoDB server, connect it to the primary, and what it will start doing is to copy all of the data to itself so that it has a copy of the database, and then it starts replicating, so it's live as a secondary. So this is very user-friendly and easy. And the DBA basically doesn't have to do anything else than waiting. But sometimes you have to wait a really long time. So, of course, like a simple question is, what if you have a 2 terabyte database and forget about MongoDB, but just copying a 2 terabyte file over the network? It's going to take probably some hours, or at least close to 1 hour in the best case, if you have a really fast network and servers are close to each other. In the case of MongoDB, and this is kind of the bad guy in this story, the secondary also has to recreate all the indexes, so not just copy the raw data, but you need to create the same indexes as you have on the primary. So in reality, what could happen is that this process could take weeks. Of course, the database is also live, so while you are copying this snapshot, there are also more, there are like new operations arriving as well, and at some point you have to replay all of those as well, so you catch up with the current state of the primary. So in reality, even like on a healthy cluster, so we have a test, I think, I say it's a terabyte, but I looked last week, I think actually it's like a 660 gigabyte database that we used for testing this. And it used to do a week. It used to take a week roughly for this test to complete, just to add another node, do nothing else. So if during this week there is like a network interruption or something, then it's broken. You have to start again. If you are overloaded, this was the test on fairly okay Amazon hardware. If you are overloaded, which often happens, usually like sometimes the reason you are adding more servers is because the existing ones are already overloaded. So then we have had cases where this never completed, and users had to do some manual workaround instead of using this automatic feature. So actually the main improvement that I'm aware of, I don't know if there was something else they improved, but the main improvement was just that when the actual copying of data has finished, of course have a number of databases, each of which has a number of collections, and each collection has one or more indexes. And the secondary would just start recreating each index one at a time. So even on a kind of medium complexity database, this can take forever, it's easy to imagine. So in 3.4, the improvement is just that you create all indexes in parallel. You're scanning through the data anyway. It's kind of stupid to then do one index and then go back and scan the same data again. So for this test case we had, the same initial sync in 3.4 now completes in less than 24 hours. Which is a big deal if you work as a DBA and you're adding a node. Now for the rest of the week you can't do any other MongoDB operations before this finishes. During the weekend you're kind of a little bit worried, is it completing or not, or do I have to start from scratch on Monday? Whereas now you kind of come back in the morning and it's finished or almost finished. So this made a big difference to a lot of real-world users as well. I've been involved in many support tickets also, where week after week it was like, now the initial sync didn't finish again, and like, how long should we wait? Should we start again? Blah, blah, blah. This is history. So the next question is, what is this balancer process? So balancer is a background process in a sharded cluster where you have, so for scaling, you partition data into multiple pieces. Each shard has a partition of the data. And this way you can load balance queries to different shards. And of course, each shard typically is highly available in itself. So in this diagram, you would really have like 3 servers for each shard, but to make the picture simpler, there is only like 1 cylinder for each shard. And in front of them, we have a mongos, which is like a proxy server. So now all your applications connect to mongos, and mongos knows where all the data is on each shard. So when a query comes in, it says, oh, actually, like to fetch this data, I can go to this shard. And for this other query, I can go to this shard. But the application doesn't need to understand how the data has been distributed in the cluster. And then we have this little database here, which has metadata about the shard, such as a collection we call chunks. Chunks are really our like mini partitions. So it's a partitioning table. And the config database itself is probably a replica set as well. So you have 3 config servers as well. So how this balancer works, again, this is like a nice ease of use background feature in MongoDB. Because now if you start inserting more data into MongoDB, maybe like some of the data will go more towards the rightmost shard, and maybe the shards on the left will get less inserts. So over time, your data is no longer balanced. So the balancer's job is to keep the cluster in balance. You can actually create some rules also how the partitioning should work, but by default, the balancer is actually quite simple. So all of your data is divided into chunks that should be roughly 64 megabytes. And then the job of the balancer is just to keep an even number of chunks on all shards. And sometimes that's all you need. Sometimes you need to add more configuration yourself to get the kind of scaling you need. So in 3.4, right, in 3.2, the balancer process was running on the mongos, which is this in itself a stateless proxy process. But the problem is that in practice, users have many mongoses, at least 2 for high availability, but for a large cluster, you might have 100 or so. And because they are stateless and identical, each of them is actually running a balancer process. And then they write some state into the config database, this little database server. So suddenly, in a large cluster, you had 100 mongos servers who were all trying to take a lock in the config database. And then 99 of them will fail, and then they will retry again after a while. And once one of the mongos actually succeeds in taking the log and does the balancing, then after a while everybody has to also reload the data to try to balance the next chunk. So this was not a huge problem, but it was certainly unnecessary that all of these mongoses were trying to lock each other. So in 3.4, the balancer is simple. This balancer thread was moved to the config server, and in particular the primary, when the config database is a replica set, it is running on the primary. And there is exactly one primary config database in a sharded cluster. So this way we have only one balancer process, and it doesn't, in a way, need to lock anything at all, because you already know there is only one. So as long as it's just keeping track of its own state, you are fine. So that was it. There was like no performance results. But it's kind of obvious to see that it removed some unnecessary contention, which sometimes then actually you might see like some blips in production where you might see effect of this when you are doing actual queries in MongoDB as well. All right. Again, a very simple feature, compression of wire protocol. So we already use Snappy and Zlib. By default, it's Snappy to compress data on disk. And in 3.4, we have also added this to the network layer between servers, but not between client server. That is in 3.6, I think. So in 3.4, again, if you have a replica set, and some of the replicas are on different continents, and you need to sync 1 terabyte to another secondary, it's actually quite a huge deal. Snappy compression could be 4 times or even like 5 times on data that compresses well. So in this case, the replication will be 5 times faster, because in this kind of wide area cluster, by far the biggest bottleneck you have will be the network bandwidth. So again, this is something our team wasn't heavily even testing. Somebody just kind of implemented this. You add a library call to the networking stack, and everybody, all the users are happier, but we didn't like heavily test it. It's kind of obvious that in some use cases it made a huge difference. And in some others it makes no difference if you have a local cluster. Balancer throttling. So this is a more interesting one. Of all the boring improvements, this is the most interesting one. So what is this throttling? So the balancer in a sharded cluster that we talked about is a background process. In theory, it's kind of transparent, so you don't see it, but of course there is some overhead, because what it is doing, it's inserting 64 megabytes on one shard, and then it's deleting 64 megabytes on another shard. Especially until MongoDB 3.2, we had a database engine that wasn't actually very efficient on concurrent writes. So if you have like a background thread that's suddenly going to write 64 megabytes worth of data, actually it's not very transparent, so it will cause a lot of locking in earlier versions of MongoDB. So to make this less disruptive, the balancer thread was designed to be throttled. So first of all, there is only one balancer thread concurrently in the whole sharded cluster. And then essentially it does the same thing as a write concern 2, which means like after you write a document to the primary, you also wait until replication has happened. So in this case, for the purpose of throttling, we don't actually care about durability on this point. There is like a commit of this balancing later on, where we do care about durability. But in this case, we don't care about durability. We only wait for the replication to have like a pause. So if the secondary is on another continent, you actually wait much longer. If the secondary is close, you wait shorter. So it could have been asleep, but for some reason it was implemented like this. So now actually we have made the balancer really slow on purpose, because, I don't know, 64 megabyte of documents, so we are talking about at least some 100 of documents or more if the documents are really small. So between each document, we are now going to sleep for 1 or 2 milliseconds, or 100 milliseconds if we are talking about a wide area cluster. So already in 3.2, this throttling was configurable, but by default this was on. And in 3.4, we have then changed the default so that if you use the WildTiger engine, which has better write, like it's capable of handling more write performance, then we actually turn off this throttling, which is called secondary throttling because it's kind of tied to replication. And like we already said, also new in 3.4, The balancer is now running on the config server, so it's less complex. And the other improvement that I will talk about separately, that instead of one thread per cluster, there is actually one thread per shard. So each shard can actually be involved in either an incoming or outgoing migration. And just to clarify, so for durability point of view, at the end of the chunk, there is like an additional W majority commit to make sure. So we don't want to kind of move data from one shard to another, and then there's a failover, and suddenly you lost 64 megabytes of data. So this is written as a durable commit, but it's sufficient to actually do that after the last insert has happened. Right, so to talk about the throttling, there are actually a couple of things you do to configure the balancer. And it depends on the user which way you want to go. So users actually have both problems. So sometimes, even when we had the throttling on, we have users who are so much at max capacity, and bear in mind that this might be a reason why they're adding more shards, because their current cluster is already maxed out, and in fact it was maxed out half a year ago, but they kind of tried to save money as long as possible, and then when they applied for more budget, it took them some months to get approval for the budget, and then it took them some months to get the servers online. And now, you know, they are adding more shards, but it's really late, and they are really, the existing shards are really overloaded. So then when they add the new shards, the balancer kicks in and is going to migrate not just 64 megabytes, but continuously, maybe like terabytes of data. Then this makes the situation worse, because suddenly you have a lot of inserts and deletes on a cluster that was already overloaded anyway. So some users actually don't want the balancer to go faster, they want it to go even slower. So what you can do is we have a balancer time window. So many services have peak hours, and then you have more silent hours, for example, during the night. So you might set the balancer window that runs from midnight to 6 a.m. or whatever is your kind of less stressful time. And then, oh, sorry, it was already in 3.0. You could configure this secondary throttling and write concern by writing a settings document in the config database. So this is the example, but essentially I've never really understood why there are two. So there is like a secondary throttle that you set to true or false, and then I also set the write concern to 1. But I would expect that if I set this to false, it kind of implies that write concern 1 is used anyway. So, but I don't know. I set it to 2 because I set both of these because that's what the manual says that I should do. So this was actually something I can benchmark, and I have some interesting results. And I did this on 3.2, but essentially what I'm showing here is what is the default experience on 3.4, which was an improvement in 3.4. This is a fairly lightweight benchmark, like kind of on my laptop, more or less. YCSB load with 30 threads, a small batch size, and 3 shards. Sorry, this was not on my laptop, of course, so this has been on Amazon. And yeah, on C3 large instances, so fairly small instances by my standards. And the throughput here has been varying from like a couple of tens of thousands of documents per second. So again, I want to say this is like a quite small. In fact, that's the whole point of this benchmark, is that this is like a typical beginner setup, which is not optimal experience, but it creates stress on the balancer, and we will see how the balancer can handle this suboptimal situation much better in the 3.4 configuration without throttling. So in a way, my point is not that this is a great insertion rate. In fact, it's not. But the whole point is that even with this low insert turn rate on the 3.2 defaults, we get into trouble, whereas on 3.4 actually the balancer is able to handle it. So what we end up is this kind of graph. So this is not about the rate of inserts per second, rather I have 3 shards, so I have 3 lines which show the number of documents on each shard. And what happens, so the challenge with sharding is that you need to actually understand what your application is going to do when you choose the partitioning scheme. So the default sharding is by the ID, and many applications and many benchmarking tools like YCSB will insert documents with an increasing ID. Right? 1, 2, 3, 4, 5, 6, 7 is the ID. And now we have partitioned ranges, it's range-based partitions. So the lowest range is on one shard, and the second one is on the second shard, and the third one is on the third shard. But the IDs keep increasing. So actually all of the inserts will always go to the last shard or first shard, depending on which way they go. And that's exactly what we see here. So actually all of my inserts are going to this shard. And then in the background, the balancer is seeing that, oh, I have all the data on this shard and nothing on the 2 others. So I'm going to start in the background moving documents to the 2 other shards. This is number of documents. And you can see the curves are quite smooth. And this is the number of chunks, which is a funnier graph. And you can see that even though the growth in amount of data is actually quite smooth, the chunk is actually metadata. So there is another process that kind of splits chunks once in a while when it says that, oh, actually this chunk has like half a gigabyte of data instead of 64 megabytes, so now I'm going to split it into smaller chunks. And that's why you see these kind of jumps once in a while, because the chunk splitting process wakes up and creates a lot of new chunks. And then the balancer sees, oh, there are lots of chunks here, I should move them around. So it's both uneven, and even when it's trying to do work, it is falling behind compared to the one shard which is receiving a fairly light amount of inserts from the YCSB benchmark. So now we turn off the throttling to set it to false, write concern 1. So this means the balancer can move data much faster. And what we see is actually that more or less we have the same amount of data on each shard, even though it was the same kind of naive insertion benchmark that I did in the first case. So this means for a kind of typical application workload, which is not heavy, like this is not a high performance configuration, this is just a workload that some application developer wrote and put into production. The balancer is actually able to manage the situation, and you end up with a balanced sharded cluster. So this is great news. What did we learn? Is there something I haven't explained already? Right, so the default since MongoDB 3.4 is with throttling off. So we have much more users who will not get into these weird situations. It is still the case that if you do set up this kind of test and you want to see, like, now I have sharding and I expect to get much faster inserts, if you do it this way, you will not get any faster inserts that you would get with a single server, whether it's MongoDB or a relational database. So to actually get the benefit of more performance, like with 3 shards you would expect 3 times more inserts per second, then you need to partition, for example, with a hashed shard key so that writes go evenly across the cluster. The last one, not quite trivial either, parallel chunk migrations. So with all these improvements, 3.4 was already quite a good release. And we have this chunk balancing going on. It's much faster than before. But in reality, we have customers which have more than 2 or 3 shards. So for example, 10 in this picture. In reality, we have customers who recently went from having 50 shards to having 100. So quite typically, you don't add one more shard, but you like double because you are having exponential growth or so. So what happens if I have 10 shards and add another 10 shards, and I have one balancer process in the entire shard who is moving one chunk from one shard to another, and the 9 other shards are still empty. So it's going to take forever, especially for the customer with 50 new shards, before all of the 50 new shards have any data on them. So again, quite a simple change in MongoDB 3.4. Now you can actually have n per 2 migrations at a time. So essentially, each migration can be either donor or receiver. Each shard can be either donor or receiver of a migration. So if you add 10 new shards, you can actually have 10 threads balancing at a time. So actually, this will complete just as fast whether you added 1 shard or whether you had 10 or whether you had 50. All right. Oh, this is a nice animation, but here we have some information. So what we did in 3.6, these are kind of just some additional small tasks. This was not a huge focus in 3.6 anymore. But one of the things related to balancing is also like when I have inserted data to the new shard, I need to delete them from the old shard. So this was a little bit optimized as well in 3.6, so it has less overhead. Is Misha here already? No. All right. Secondary reads in a sharded cluster. This was maybe not so well known. It's also related to the orphans. So essentially, you can imagine during this migration, we will be in a state where you have inserted documents to the new shard, but you have not yet deleted them on the old shards. And MongoS and actually like the primary on each shard have some additional logic to filter out documents that are already here but are not actually yet supposed to be on this shard. So they compare against this metadata which chunks actually are on this shard, and if you find some documents in a query which are outside of these ranges, then you actually don't return them to the client. And this way we get correct results. But this logic only existed on primaries. Now in 3.6, after all of these years, you can actually query secondaries on a sharded cluster and get correct results. So that's nice. I don't know if people here were aware of this. So you can easily query secondaries if you have a replica set, but once you move to sharding, you should actually stop reading from secondaries because you might get like double. Typically what you see is too many results. There are some other tasks that are not yet in 3.6, so I don't know when they will be done, but just kind of to mention what could still be done in this kind of theme of boring improvements that make the DBA happy but not marketing. Make initial sync somehow resilient, so maybe it can continue if initial sync was interrupted after 5 hours. You don't have to start again, but you can continue from where you got before. So that would be great. And the other thing that is still happening, actually I'm not sure if it's on MongoS anymore, but I think it's probably the thread on a config server that is also doing this chunk splitting. But that could actually be done on each, that could be the responsibility of each shard. That would because each shard is more aware of how much data it is receiving and deleting, whereas the current logic is actually based on a estimation. So the MongoS kind of sees that data is being inserted and deleted to a shard. So it's kind of keeping count, and after the counter reaches some value, it says now the amount of data on this shard has grown, so I'm going to split some chunks. But actually the MongoS doesn't see, because there are other MongoSs, the MongoS doesn't actually see the whole truth, whereas the primary server knows precisely how much data it has inserted and deleted. So that would also be, from an accuracy point of view, a good improvement. In practice, it's actually not a problem that these chunks are inaccurate, whether they are 64 or 100 megabytes or whatever. As long as the balancer keeps moving them around, it's usually quite okay. And then, of course, chunk migrations still are not optimal, or I would say as fast as possible. I don't know if it's actually desirable to have them as fast as possible, but of course it would at least be nice to have the option of going even faster. So even if we remove this throttling, it's actually still inserting one document per time, but in MongoDB you can also do batch inserts or bulk inserts. So you could just take the whole chunk, or maybe not 64 megabytes, but you take like 1 megabyte at a time and just insert lots of documents. That's going to be faster. And maybe we can have more than one per shard. So now, of course, it's good that we have one thread per shard, but you might allow somebody to have 2 or 3. Especially if you have, if you had empty shards, there is no queries going to them anyway, because there's no data there to be found. So I think you could go like at max speed until they actually become active. So you could probably do that. I think that was all. And I'm again 2 minutes ahead of time. Both of my talks today were like perfect timing. Now we can do questions. Thank you.
Yes, thanks for your talk, Henrik. I have 2 questions. The first is, can you exactly explain what does this secondary throttle option mean? I mean, when it's off or when it's on, what's the difference? And
Right.
the second question is about the explain method on aggregation pipeline framework. Are there any plans to improve this? Because explain method on simple find queries, it's much more functional.
Oh, is it still not fully functional on aggregation?
I think it doesn't show execution stats or some more complex
All right.
query statistics and stuff.
So
Thanks.
to the second question, I don't have an answer right now.
Okay.
I actually thought they were already equal.
I guess no.
Yeah, I'm sure that's the case. And for a long time there was no explain for aggregation, and that was fun to be a consultant trying to fix queries. So your first question was related to throttling, which comes, it's number 4. So, here it is. Yeah, so first of all, how you configure it is like this. So this is a bit different from most other management things in MongoDB where you kind of execute some command which does the configuration. And this is actually something where you edit something in the settings collection, which is quite unusual. And but you do this update, that's fine. The funny thing is that after you do this update, you don't know when exactly the balancer reads this new setting the next time, but it's kind of soon after you have done this. And right, so what does it mean? So a chunk, we move one chunk, it's 64 megabytes, so let's say it's like 100 documents, for example. With the throttling on, it means I take one document, insert it, and use write concern 2. So basically I have to wait for one replication to succeed, and then I continue, insert the next document, and so on. So with the 100 documents, even with fast replication, I would expect this to take 100 milliseconds, 200 milliseconds to move 64 megabytes. When you set secondary throttle to false, I insert one document at a time, but I don't wait for the replication. So as soon as I've inserted one document, I insert the next one. And the optimization I was kind of like that is on my wish list on the last slide is I would just take 100 documents and insert all of them at once. But this doesn't exist. In a way, I'm okay to, although I didn't know the answer to your other question, but I'm actually okay to answer any MongoDB related questions if you happen to have some.
Thanks for your talk.
Thank you.
I have a question that might have no concern to your talk, but the load balancer is mongos. Yes?
Not anymore. In 3.2, the load balancer was on mongos, and in 3.4, it is moved to the config server, the primary config server. Yes.
Well,
and this is because there is only one primary config server, and we only need one balancer, so this is like a good place to have it.
My question is that server durable? I mean, can it be as a bottleneck in my cluster and so?
Right. I think that's two questions, if I understand you correctly. So the balancer can be, or the balancer can cause overhead in your cluster, like I said, if you have a very overloaded cluster, and then also the balancer starts moving data back and forth, then this adds more load to your cluster. So sometimes this makes a bad situation worse. And in this case, you can turn the balancer off, or you can have it running only at some times during night, for example, so it doesn't affect most of your users. So I think you asked also about durability.
Exactly.
Yes. So where is that slide? So that was the last. That was kind of not the focus of my talk, but it's a very important question. That whether or not you are doing this throttling. So first of all, the balancer is moving these documents in the background, and while it is inserting, let's say we have a chunk of 100 documents, while it's inserting, let's say 55 documents, if you query, if you have an application that does a query, the documents are still like officially on the old shard, on the original shard, and the query will be routed to the original shard, and you will find all of the 100 documents there. And even if you have a query which will go to the new shard,
not a donor shard. Yes? Not a donor shard.
Yeah, the old shard is the donor shard. So let's say, and if you have a query which will also be routed to the new shard, which is the recipient shard, and let's say it's also like completely empty. Let's say we added a new shard and it's empty, and the balancer has inserted 55 documents, but the migration is still ongoing. The new shard will actually return 0 documents. So there is logic on both of the shards to say that even if there are physically already some documents inserted, the shard will know that this chunk doesn't actually yet exist. Like in the partitioning table, this chunk isn't yet mine, so I will ignore these documents that don't belong to me, even though the query actually found them. I wonder if this is easy or difficult to understand. So when the balancer has completed inserting all 100 documents, what it will do, where is this nice picture? So let's say this small blue thing is one chunk. So now all of the documents have been inserted to one chunk. Now it will write to the config.chunks collection to say actually that this chunk is now on the middle shard. And after this, all queries will be routed to that shard. and then and that is when that is why it happens atomically. So this has been supported like long time ago, before we had any kind of transactional engine or anything in MongoDB. The kind of atomic moment when the migration has happened is when you update this single pointer in the config.chunks collection. And from that point on, you will have all queries to go to this shard. And now you have the same documents here, and the same thing will happen here, that if you have a query going to this shard, it will still find these documents, but it will say that, oh, actually, like this chunk doesn't belong to me, so I will ignore these documents and not show them to the client. And then, of course, eventually in the background, we also delete the documents from here so that we can reclaim the space. So then they are also physically deleted. Was this answering your question?
Yes, now I see. Thank you very much.
Cool.
Thank you for your speech. I have a question about stream compression between server. Is it really stream or just compress some chunks? And the second question about, do you have to some ideas to implement a new compression algorithm, some zstd?
Right. First question, I don't know how it was implemented. I would expect that it compresses it compresses whatever kind of blocks of data are moved internally. But probably not as a stream. It's probably staged somehow. Do we have plans to implement set STD? Yes. So for disk encryption, there already is. We have already tried this for Wired Tiger. And there is I think there is something with like just building this library. There was some complexity that didn't work out of the box, and it wasn't high priority, so it's not actually in 3.6. It does work, but it's kind of something boring to do with building or linking or something that nobody prioritized to do. But then of course this, like having it for the disk doesn't, then doing it for the network is again a different task for some other team.
Thank you.
Yeah. I should say we do get good results with the ZSDD, but apparently not as good to actually prioritize it to get it to the product.
Back to the balancer.
Yes.
Just to conclude the question, so if I want to try to get the least impact on my donor shards while balancing, I can set this secondary throttle to true, and as well I can set W to 1 if I'm not too concerned about the consistency while migrating.
The consistency is different.
Mm-hmm.
So like it's consistency, and I suppose it relates both to consistency and durability. So these happen at the end of, like after the last insert of the chunk. There is always W majority, and this is hard coded. I've seen it in the source code, so you cannot configure it. It's always W majority for durability reasons.
And on the next slide, you had it like. And the next
that's why this is so confusing. So this is not. This does not affect that.
Okay.
Yeah, I think you can. So if you set secondary throttle to, I understand where it should make sense. If you set secondary throttle to 2, and you set this to more than, this is true, and you set this to higher than 2, then probably, like if you have like 7 secondaries, and you set it to 6, then this will make it even slower than if you set it to 2.
Mm-hmm.
It's kind of like, essentially they could have just used sleep to do the same thing. I don't know.
Mm-hmm. Okay, thank you.
Oh, I know one. Yeah, I know one reason why it could be tied to replication. one thing, of course, that happens on a replica, like on an overloaded replica set, one thing is also that replication becomes slower. So having the delay tied to the replication round trip in a way might make sense. So you kind of, the delay is dependent on how slow your replication is.
Давайте последний вопрос.
Hi.
Hi.
Thank you for your speech. I have a question about hardware on the config server. We move balancer on the config server, so we must change the hardware.
No, the data doesn't go to the config server. It's just coordinating it.
There is no overhead on that.
It's just one thread. It is just telling the shards what to do. It's not, the data is moving directly between the shards.
Окей, спасибо всем большое, что слушали. Давайте поаплодируем, поблагодарим.
Thank you.